Hello, I'm Brian Young, and today we're doing Module 26111, Residential Wiring. Let's get started. Module 26111, Residential Wiring. Successful completion of this module prepares you to do the following. Explain how to size the electric service for a dwelling. Identify the grounding requirements for a residential electrical system. Explain how to install service entrance equipment. Identify wiring methods for various types of residences. Explain how to lay out branch circuits and size outlet boxes, and explain how to select and install various wiring devices. Performance tasks, your instructor is going to have you give the size and list of installed major appliances for residential dwelling, demonstrate or explain how to compute the lighting, small appliance, laundry loads, compute the loads for a large appliance, uh, determine the number of branch circuits required and size, and select the service entrance conductors, panel boards, and protective devices. Using an unlabeled diagram of a panel board, label the lettered components, select the proper type and size of outlet box needed for a given set of wiring conditions. Overview. Faulty wiring in a home can cause big problems. To avoid these problems, it's important you understand the basic steps for planning and installing a residential electrical system. These systems include heating and air conditioning, lighting, and household appliances. In this module, you'll learn basic load calculations and the NEC requirements for residential electrical systems. You'll also learn how to lay out branch circuits, install wiring and wiring devices, and size outlet boxes. When you install an electrical system in a residence, you need to bear in mind that you are keeping the population safe. It's not just making sure that what you wire today is going to be there in a year when the warranty runs out. It's going to be there for 20 years, 30 years. And you want to make sure that the work that you do today is going to be safe for 30 years. You want to make sure that that end user, John Q. Public, they don't know anything about electricity. They don't know anything about circuit breakers. They don't know anything about receptacles. All they know is they can plug in and turn something on and it works. All they know is they can flick a light switch and the lights come on. You have to make sure that your installation meets all federal and local codes and that it is a safe installation and will be for years to come. I cannot stress that enough. So let's get into this here. 1.0.0 Sizing Residential Electrical Service. Explain how to size the electrical service for a dwelling. Describe electric service and appliance loads. Summarize how to apply demand factors. Describe how to size the load center. And then there's some performance tasks that your instructor is going to want you to do. First electrical system provided is interior lighting. Now we use electricity for everything from powering our internet connections to running appliances for washing our clothes. In this section, you'll use a typical residence as a model for sizing the electric service according to the latest edition of the National Electrical Code. Always refer to the latest edition of national, state, and local codes in effect in your area. So again, I'm using the 2023 National Electrical Code. I'm going to do this a little bit differently. I'm going to look at the code book first. Let's read what the code book has to say, and then we'll come back to the book, and I think you'll have a better understanding of what is being put forth in this module if we look at the code book. So here's NFPA 70, 2023, and again, if we go to the table of contents, we'll notice that Article 220 is branch circuit feeder and service load calculations. So that's page 92. Let's see if we can find page 92. Again, I'm going to go a couple of pages past 92. There's Article 220, branch circuit feeder and service load calculations. So the first thing that they talk about is general lighting. Let's draw a residence. And this residence isn't going to be a work of art, so forgive me. But we're going to make this general. So here is my house. It's 30 feet by 40 feet. I'm going to say that it has a carport, and I'm not going to worry about the carport because it doesn't count toward square foot area of the house. Has a bedroom and maybe another bedroom. Oops, the other way. And maybe this is a bathroom. I keep making the doors the wrong way. Doesn't matter. Tub, sink. Maybe this is a toilet. Maybe the sink. I don't know. It all fits in here. Don't worry about it. But when we talk about general lighting is all of the lighting circuits and all of the receptacle circuits throughout the house. So we use those receptacles for general lighting. You have a room, you have an end table, you put a lamp on that end table. Well, that lamp is going to run off of the receptacle circuit. So we're going to figure the general lighting load for the entire house. The way the code tells us to do this is square foot area of the house times 3 volt amps per square foot. Okay, so in this case we have a 30 by 40, 30 feet times 40 feet is 1,200 square feet. Okay, well, we would take our 1,200 square feet times 3 volt amps, and we would get a net load of 3,600 volt amps for general lighting. That's our general lighting. Then we also have in the kitchen, here's the refrigerator, here's the countertops. Let's say this is the sink by the window, and let's say this is the range. Well, we have receptacles around this kitchen on the countertops, and those receptacles are on 2 branch circuits. It's a minimum of 2 small appliance branch circuits in the kitchen. 2 small appliance branch circuits. At 1,500 volt amps each equals 3,000 volt amps for our small appliance branch circuits. And then we have 1 laundry circuit. Somewhere in this house, we have to have a 120 volt, 20 amp receptacle. Maybe there's a utility room. Maybe there's a utility room off the kitchen, and it has the washer dryer. So in here, we're going to have a dedicated circuit for laundry. Okay. And that laundry circuit is also rated at 1,500 volt amps. I hope you can follow this. I hope that I'm not writing too sloppily. I'm trying not to spend 6 hours on this. There's 1,500 volt amps. So between the general lighting, the small appliance branch circuits, and the laundry load, we have a subtotal 6 and 5 is 11, 4 and 3 is 7, 1 is 8. We have a subtotal of 8,100 volt amps so far for our house. And then what is it? 220/42 that tells us that we can take the first 3,000 volt amps at 100%. So here we've got 3,000 volt amps. And then it says the next 3,001 to 120,000 volt amps is at 35%. So if we deduct 3,000 amps from this 8,100, we've actually got 5,100. So the next 5,100 volt amps at 35%. And for that, I'll use my calculator. There, oh, come on. There. So we've got 5,100 times 0.35, 35%. It's 1,785. So that's what we've got. We've got 1,700. Whoops, wrong. What happened to my color here? 1,785. 1,785. So for everything we've talked about so far in this house, the general lighting, the two small appliance branch circuits, and the laundry branch circuit, we have to supply at the meter 4,785 volt amps just to serve those loads. We haven't talked about air conditioning or heating. We haven't talked about the range. We haven't talked about appliances like the water heater or a disposal or anything like that. That's the beginning of our calculations. Now, let me go into the code book and let's see what the code book tells us. Here's looking for 22012, but it's not going to be in 220.12. It's going to be in, oops. Here's 22042, general lighting load by non-dwelling occupancy. Where's J? Show window lighting. Where is it? Track lighting receptacle loads. Where did I put it? Where did I set that? All right. 220.41 dwelling unit minimum unit load. In single family, two family, multifamily dwellings, the minimum unit load shall be not less than 3 volt amps per square foot. And again, I don't use metric, I use the standard SAE. So 3 volt amps per square foot. Unit loads include the following lighting and receptacle outlets, and no additional load calculation shall be required. All general use receptacle outlets of 20 amp rating or less, including receptacles connected to the circuits specified 210.11 C3 and C4, the receptacle outlets specified in 210.52 E and G, and the lighting outlets specified in 210.70. The minimum lighting load shall be determined using the minimum unit load and the floor area as determined in 220.5C for dwelling occupancies. Motors rated less than an 1/8 horsepower connected to a lighting circuit shall be considered part of the minimum lighting load. So 225C, I think they're going to tell us to use the outside floor area. There you go. See, the floor area for each floor shall be calculated from the outside dimensions of the building, dwelling unit, or other area involved. For dwelling units, the calculated floor area shall not include open porches or unfinished areas not adaptable for future use, such as a habitable room or occupied space, occupiable space. So they're saying we would take the dimensions on the outside of the house. You can measure the house on the outside. And just like we did our 30 feet times 40 feet, we got 1,200 square feet, same thing. We've got 1,200 square feet, and it told us in 22041, then it's 3 volt amps per square foot. So 1,200 square feet times 3 volt amps per square foot was 3,600 volt amps. Okay, remember that's volts times amps. And then we also have the small appliance branch circuits in the kitchen. And we have the laundry load. And we need to add those in. Here's 22052 small appliance and laundry load dwelling unit. The reason we're calculating these now is because they're included in this 22054 demand factor. Okay, and it'll tell us that. A small appliance branch circuit load. In each dwelling unit, the load shall be calculated at 1,500 volt amps for each 2-wire small appliance branch circuit as covered by 210.11c1. Where the load is subdivided throughout 2 or more feeders, the calculated load for each shall be included not less than 1,500 volt amps for each 2-wire small appliance branch circuit. These loads shall be permitted to be included with the general lighting load and subjected to the demand factors provided in Table 22045. I'm sorry, I should have said 50, well, okay, 22045. Where is 22045? Here it is right here. There's 22045. And 22045 for dwelling units tells us the first 3,000 volt amps is at 100%. And from 3,001 to 120,000 is 35%. Anything higher than that, which don't be mistaken, anything over 120,000, we would calculate at 25%. And then the laundry circuit says the same thing. It says a load of not less than 1,500 volt amps shall be included for each 2-wire laundry branch circuit installed as covered by 210.11c2. This load shall be permitted to be included with the general lighting load and shall be subjected to the demand factors provided in Table 22045. So that's what we did. We took our 1,200 square foot area times 3 volt amps, got 3,600 volt amps, and then we added 3,000 volt amps for 2 small appliance branch circuits in the kitchen. That's 1,500 volt amps each, and 1 laundry load, 1,500 volt amps. When we added all 3 of those together, we had got 8,100 volt amps, and then we used Table 22045 in order to find the demand factor. 3,000 volt amps, the first 3,000 volt amps at 100%, and the remaining 5,100 volt amps at 35%. Okay, so let's go into the book and see what the book says. Residential electrical service load as you gain experience. I'm not going to read all this. Your choices will be guided by many factors, including the wiring method, the overhead or underground electrical service, type of building construction, the service entrance and equipment, the grade of wiring devices and lighting fixtures, selection of lighting fixtures, type of heating and cooling system, control wiring. All of these things will go into determining what the specific location of these branch circuits will be, or where the panel will be. Let's see what a service entrance is. They have that highlighted. The point where power is supplied to a building, including the equipment used for the purpose. The service entrance includes the service main switch or panel board, metering device, overcurrent protective devices, and the conductors, raceways for connecting to the power company's conductors. So that's the point of service, where our masthead or our service mast and the weatherhead, we bring 3.5 feet of cable out, and at the point where the power company is going to meet up with our wires and put butt splices on there and crimp connectors, they're going to tie that together. That's the point of service. That's where we get our service. So let's see what they say here. They say, in a residential occupancy, the utility company will provide a 120, 240 volt single phase service entrance. The service and feeder will be 3-wire. Each branch circuit will either be 2 or 3-wire, and each safety switch, the service equipment and panel boards, will be 3-wire with a solid neutral. On each project, you must consult with the local utility to determine the point of attachment for overhead connections and the location of metering equipment. So the incoming service ties in at this point of service into our feeders. Our feeders go down to, well, I want to change that. Our service entrance conductors go from the point of service to the line side of the meter socket. The feeders go from the load side of the meter socket into the panel, and consequently any other subdivision, if we have a secondary panel, if there is a second floor and we're required by code to have a panel on the second floor, then we will serve it with a feeder. A feeder goes between overcurrent protection devices. So between the overcurrent protection devices in the main panel and those sub-panels, those are feeders. And if you go out to the AC unit, the air conditioning compressor outdoors, if you put a fused disconnect outdoors, those are feeders technically supplying the fused disconnect. The branch circuits are from the last overcurrent protection device to the utilization equipment. So using that air conditioner as the example, from the fused disconnect to the air conditioning compressor, those would be a branch circuit. So the feeder is any circuit conductors between the service equipment, the source of a separately derived system, or other power supply source, and the final branch circuit overcurrent device. When you're talking about going to the utilization equipment, it's called a branch circuit. A portion of a wiring system extending beyond the final overcurrent device, protecting a circuit. So feeders go between overcurrent protection devices, and branch circuits are from the final overcurrent protection device to the utilization equipment. It says in many cases the service, the main disconnect panel board of service conductors can be sized using the NEC before you locate the outlets. In other cases, you'll have to lay out the outlets first. However, you'll always have to decide where to locate the service entrance panel board before you can install the circuits. That way you know in which direction and at which point the circuit home runs will terminate. All right, 1.1.1, calculating the residential electrical service. Let's calculate the service load. Start by looking at the floor plan. A floor plan is a drawing that shows the length and width of the building and the rooms it contains. There's a separate plan for each floor. Figure 2 shows how to develop a floor plan for a single-family home. So here's your floor plan for this single-story home, single-family home. Basically, the floor plan is where they cut the roof off at the top of the windows, and then you can look down inside of the home. And this is what's drawn on the paper. That's your blueprint. And this is what it looks like. The only thing I would say is that this column, because it's in red, should have shown up over here. There should have been a little square showing that column. There's the resulting floor plan is what remaining structure looks like when viewed from above. Now look at figure 3, which shows the floor plan of a 2-bedroom home. The building's built on a concrete slab with no basement or crawl space. There's an unfinished attic above the living area and an open carport just outside the kitchen entrance. So here's the carport. The carport does not count as square foot area for calculating the square foot area of this house. Their house is 48 feet by 33 feet. So we'll multiply those together, 48 times 33, and then we'll subtract this 19 foot 6 inches by 12 foot. We'll calculate that and subtract it because it does not count as living space. It's important to know the electrical load when planning an electrical service so you know the type of service to install. In this module, we use the worksheet provided in Appendix 26111-23B, similar to the one in Figure 4, to compute the electrical load requirements for this residence. So here they have general lighting load, square foot area of the dwelling. They went ahead and calculated it for us. It's 1,350. We can check that. Let's check that. So they said it was 48 times 33. So 48 times 33 equals 1,584. And And then we're going to subtract from that 19 foot 6 times 12. So minus, I'm going to open a parenthesis and say 19.5 because it's a half a foot. So I'll use 0.5 feet times 12 feet, close parenthesis, equals. Oh, what did they do wrong? Hold on, 19.5 times 12 is 234. So let me try that again. 234. So they had 48 times 33. 48 feet times 33 feet is 1584. What was that other number? 234 minus 234. There you go. 1350. All right, that's good enough. That's what they came up with. 1350 feet times 3 volt amps per square foot. Remember, 220.41, there it is right there, NEC section 220.41 is 4,050 volt amps. Remember, a volt amp is a volt times an amp. So when we get finished with our calculations, we'll divide by 240 volts, and that will tell us how many amps. And we have 2 kitchen small appliance branch circuits. The code tells us we have to have a minimum of 2. You can have 3, you can have 4, you can have more than 2 small appliance branch circuits, but you have to have a minimum of 2 per kitchen. If you're building a big house and you've got 2 kitchens, you have to have a minimum of 4 small appliance branch circuits, 2 in each. So that was 3,000 volt amps, and then the laundry branch circuit at 1,500 volt amps is 1,500 volt amps. So then they added these all together, and they got 8,550 volt amps. But remember, they went to table 220.45. They took the first 3,000 volt amps at 100%. So that's 3,000 volt amps. The remaining 5,550, they multiplied times 35%, which gave them 1943. And then when we add those together, we get 4,943 volt amps. So that's our load so far. Then they're going to go on to talk about fixed appliances. If you have 4 or more fixed appliances, you're allowed to derate to 75% of the nameplate rating of those appliances. If you only have 3, then you have to stick with 100% of the nameplate rating. But here's a water tank. This is a hot water heater, and it's 4,500 volt amps. Here's a dishwasher at 1,500 volt amps. Here's a garbage disposal. And if we look it up in the table 430.248 for single phase 120 volt motors, it says a half horsepower motor draws 9.8 amps. So we'll take 9.8 times our 120 volts, and we get 1176. Same with this mower, this blower motor. It's a 1/3 horsepower, and we found that it was 7.2 amps. So 7.2 amps times 120 volts gave us 864 volt amps. We'll add all of those together, and we get 8,040. Now, they said if we have 4 or more, we're allowed to derate to 75%. That's in the code book 22053. We'll read that when we look at the code book. If 4 or more fixed appliances, take 75%. So 8,040 times 75% is 6,030. That's what we have written here. Other loads, well, they're saying that we have an electric range, and that's 8,000 volt amps, an electric dryer at 5,500, an electric heat. You have heat and AC, so whichever one is the larger of those two, you would use. And then the largest motor was this half horsepower disposal motor, 1,176. We have to take an additional 25% of the largest motor load, 125% of the largest motor plus 100% of all other motors. So that's what we did here. We added 25% of that largest motor load, 294. So the total volt amp demand, we added everything together. We added the 4,943 with the 6,030, 8,000 and the 5,500 and the 294. And I'm not going to check their math. I'm going to take it on faith that it's 24,767 volt amps. Now let's divide that. 24,767 volt amps divided by 240 volts. Volt amps divided by volts equals amps. 103.195833333. So I would just call that 103.2, or I would even round up to 104 amps. So they've got 103 amps here. Service overcurrent device and the minimum size grounding electrode conductor have to be rated for 110 amps. The American wire gauge per NEC section 310.12, NEC section 220.61, and table 310.16 for the neutral will give us the size of our wire. We have to find a wire size that's good. Well, because it's a residence, we're going to look at that. I think it's 310.15B7 used to be. I think it's changed in this code, but they're going to tell us that we're allowed to use a slightly smaller wire. We have to provide for 83% of this 110 amps. And since it's 110 amps, we would go up to the next highest size of meter socket. So we would have a 125 amp meter socket with a 125 meter, and our panel would be good for 125 amps. And we'd probably put we would put a 125 amp main in this panel, but I would never recommend that. I would never recommend that. If I had a service this close to 125 amps, they're saying that we need 110 amps. I would at a very minimum put 150 amp service in, but I would probably put a 200 amp service. I don't think there's any house that I would put a smaller service in. That's only my opinion. That's not code. Maybe I shouldn't express that here, but you want to provide for future expansion of the electrical system in a house. The code says in Article 90 that it is a minimum and not necessarily for convenience or adequacy of future expansion. They say to take that into consideration. So, all right. Let's go back into the code book and take a look at the electric ranges and the dryer and the heat. And I hate to say it, but this module is very lengthy. It's going to be a very long module, and I'll try to break it up into several different movies or videos, but I'm thinking it's going to be at least 6. It's probably going to be more like 10 videos for this module. There's a lot of information in this module. Just take it small bites at a time. If I say something you aren't following what I'm saying, go back, rewind, take a look, go back in the video and listen to it again. If there are still questions, put it in the comments section. It'll help me clarify some things. I can pin a comment to the top of the comments section, clarifying anything. So let's go back into the code book. So here's our code book. We were talking about electric clothes dryer. Well, it's a minimum of 5,000 watts, and in this case, a watt equals a volt amp, or the nameplate rating of the dryer, whichever's greater. So if you install a dryer and it's only 4,500 volt amps or watts, you still have to provide 5,000 volt amps. So it says the load for household electric clothes dryers in a dwelling unit shall be either 5,000 watts. Can you read that? Let me see if I can make this a little bigger for you. Sorry, there we go. That might be better. Shall be either 5,000 watts or the nameplate rating, whichever is larger for each dryer served. The use of the demand factor in table 22054 shall be permitted where two or more single-phase dryers is supplied by a three-phase four-wire feeder or service, the load shall be calculated on the basis of twice the maximum number of connected between any two phases. Kilovolt amps shall be considered equivalent to kilowatts for loads calculated in this section because it's a resistive load. Ranges and dryers, they're mostly resistive loads, so they're mostly in phase. We're going to take volt amps and watts to be equivalent. We would never do that with a motor, but for a range or a dryer, we can do that. Here's 22055 electric cooking appliances in dwelling units and household cooking appliances. This gets pretty complicated, but I'm going to give you just the simplest form, and then we'll go on from there. It says a load for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances individually rated in excess of 1 3/4 kilowatts shall be permitted to be calculated in accordance with, oops, where did it go here? Table 22055. Kilovolt amps shall be considered equivalent to kilowatts for loads calculated under this section. So again, kilovolt amps shall be equivalent to kilowatts. And here's that 22054. I don't think you're ever going to have to use this for a residence. It says 1 through 4 dryers is 100%, 5 is 85%, 6, 75%, 7, 65%. I don't think we're ever going to have a house with more than one dryer. You might have two, but I think that's pushing it. We talked about appliance loads. Here's 22053 appliance loads. It says applying a demand factor of 75% to the nameplate rating. Load of 4 or more appliances rated 1/4 horsepower or greater, or 500 watts or greater, that are fastened in place and that are served by the same feeder or service in a one-family, two-family, or multifamily dwelling shall be permitted. This demand factor shall not apply to the following. Doesn't apply to electric cooking equipment, clothes dryers, space heaters, air conditioners, or electric vehicle supply equipment. So other than your air conditioning, your cooking equipment, your water, clothes dryer, other than those things, fixed appliances are garbage disposal, water heater, dishwasher, ice maker, if you have a wine cooler some people have in their kitchen, any of those are all fixed in place appliances that you can derate if you have 4 or more. All right. So now we have to look at this table, and again, I'm only going to scratch the surface. I'm not going to go deep into this. I could talk for 6 hours on just this table. I'm not going to do that to you. So basically, it suffices to say that maximum demand in kilowatts for not over 12 kilowatt rating. If you have one range in your house and it's rated at not more than 12 kW, 12 kilowatts, the demand factor is 8 kW. Here, I'm going to blow this up. So if you have one range and it's rated at not over 12 kW, 8 kW is all you have to supply at the service. The reason for that is the code making panel, the National Fire Protection Association, the authorities having jurisdiction, they all understand that it's a rare instance when you're going to be using both burners in your oven and all 4 cooktops on the range. Maybe Thanksgiving, maybe Christmas, but most days you're going to use one burner, make some ramen, turn off the burner. You're not going to be using all of it at the same time. And when you are, there's probably something else in the house that's not being used. So they're saying that you're allowed to rate it at less than the maximum load for that range. Look, if you have 2 of them, not over 12 kW, if you have 2 ranges in your house, not over 12 kW, you only have to supply 11 kW at the service. So that would be 24 kW of possible load, but you only have to supply 11 kW. And again, this is just in calculating how big the incoming service has to be in order to safely um, service all of these loads. All right, all right. Look, there's three of them. That's 36 kW. Three of them, it's less than half, 14 kW. All right, all right. We've looked at that enough. And there's a lot of different notes down here. I'm not going to go over the notes. I think you do this again in 26301, 301. Then we'll get more in depth as to these cooking equipment demand factors. All right. So I'm going to stop here and then I'm going to start another video.